here today to talk about cold weather nitrification and how to sustain nitrification throughout very, very cold periods. And really, this is a seasonal permit. So as we get in talking to you about this particular application, we really need to look at dynamic situations from a process standpoint, but also from varying situations. And we'll get into why COD, BOD affects nitrification and fixed film system. So I have quite a few slides to go through, but feel free to stop me at any point in time if you have questions. It's mainly around fixed film technology. So it's if you're familiar with IPAS or MBBR, the first couple of slides will be a little bit of a refresher, and then we'll get more into the plant itself. So the scope of this system, this is Bloomingdale, Michigan. It is a lagoon. It was a lagoon system that had been there for many, many years, just outside of town. And they had a new permit that was issued that required them to address phosphorus as well as nitrification. Lagoon systems can do a great job at doing BOD removal, but without that additional aeration, they really can't get to a nitrification step. And they'll take up as much phosphorus as they can, but they really aren't proficient at that either. So what we were charged with in the upgrade was to build a new plant that wasn't a lagoon plant, a mechanical plant. And part of our scope was to look at putting in a headworks building to get down to 6 millimeter perforated screen. That's a critical piece of data and process equipment that you need in a fixed film scenario. As we get to the screens themselves that are in the aeration basins, you'll see that the holes that hold the media back in the tank are about 8 millimeters in media itself. So to get down to that screening, we have to make sure that any particles that come into the tank can get out of the tank so they don't occlude the screens that hold the media in the tank back. We did put in biological treatment using fixed film. It's a very compact treatment system. Takes up very little space. And when we get to talking about MBBR, it's a very robust technology that doesn't require a whole lot of operator attention. So this is a very rural community. They don't have full-time operator coverage on a day-to-day basis, so they needed a system that could be checked on periodically, but not staffed on a daily basis. To address the phosphorus issue, we ended up putting in chemical feed system that adds ferric chloride before the secondary clarifier to get additional phosphorus removal. And the land area coverage is very, very small. They had lagoon systems. They didn't want to expand greatly outside of the footprint that they already had for the lagoon system. So that's what we were charged with. And from the design criteria, a little bit different application than most municipalities, where they have really two conditions. In the wintertime, they have a boys' school that is on site, and the max design flow is about approaching 90,000 gallons per day. And what happens here is they have very high TKM load, 22 milligrams per liter, compared to their summer load, which is only 12 milligrams per liter. The difference between winter and summer, the boys' school goes away, everybody goes home, and they bring in a fruit processor. It's largely blueberries, but they also import other fruit for processing and packaging. So the flows go from 85,000 gallons peak design flow up to about 120, average design flow, 90 to about 120,000. The peak design flow can go from about 140 to 190,000. And the peak instantaneous flow relatively stays the same. We'll get to the peak instantaneous flow and why that's particularly important in fixed film design when we get to the SIB section when we talk about that. From a TSS range, it jumps up pretty good. There is an industrial manufacturer sending TSS down to the sewer, so it goes from 224 milligrams to 575. The ammonia we covered. The phosphorus, again, goes down. Not a whole lot of phosphorus in fruit processing. The pH is relatively stable, coming in as very good alkalinity in the raw water, source water. Wastewater temperature can go from 8 degrees C in the winter up to about 12 degrees C. So not a huge change in the raw wastewater coming in. And then we get into the design of the system itself. Is anybody here familiar with fixed film? Have they dealt with it before from a design standpoint? Anybody run a plant? No? Relatively new. But anyways, the way you design a fixed film process is you take, an activated sludge base, you would go by cubic feet of aeration volume. And that's how you size a plant. You take your incoming load, you look at your cubic feet of volume, how many mixed liquor solids you have under aeration, and that's how you design your system. In a fixed film system, you have the plastic media that's floating around the tank, and really you're looking at the surface area on that media and determining how much load can you put onto that surface area loading of the media. So this particular application, we had to use about 900,000 square feet of cubic media, square media surface to satisfy both loading design scenarios, both winter and summer conditions. You can see how diverse it is when we look at the actual oxygen uptake rate. In the winter conditions, the nitrogen goes up, but the BOD goes down. So the actual oxygen required in the system is only 18 pounds of oxygen per hour, compared to the summer, where we have to get very high levels of nitrification, and the BOD is a lot higher in the summer, and then so the amount of oxygen that we have to pump into the system increases significantly. So changing scenarios, very dynamic system, and it has to be robust. It does have to nitrify all year round. From an effluent standpoint, BOD all year round has to be less than 5 milligrams per liter, and the ammonia has to be less than 5.5 in the summer, and less than 7 milligrams per liter in the winter. So here are the two existing lagoons. This is an aerial view. You can see right on the outskirts of the lagoon is where we placed a whole new treatment system. If we zoom in a little bit, there's the headworks building. That contains the screen that gets it down to 6 millimeters, followed by 2 trains. This first train, these first basins in each parallel train is for BOD removal. With fixed film, unlike activated sludge, you can't do nitrification BOD in the same tank. The heterotrophs will outcompete the autotrophs, so you have to grow one bacteria on each piece of, on each zone of material. So all your BOD reduction is taking place in this stage, followed by a 2-stage nitrification system. So what we'll do generally is we'll give this a higher percent removal of nitrogen. So we're looking at about 85% removal of nitrogen through the first basin, and the remaining 15% of polishing of the nitrogen through the second basin. And then again, we added ferric chloride in between the basins, going to the final clarifier for additional phosphorus removal, and it also helps with solid settling. A new control building that houses the blowers and the monitoring instruments, the SCADA system, et cetera, in there, and a chemical storage shed with ferric chloride that pumps over. So all the piping is underground for freeze protection. So that's the new footprint. Interesting to note that biological treatment area right there is 250 times smaller than the lagoon system. So to emphasize the amount of footprint that an MBBR takes up, this is 1/250th the size of those lagoons, and it's doing BOD removal, nitrification, and with chemical enhancement, phosphorus removal. So the whole crux of a fixed film system, and when I say fixed film, I'm talking about IFAS and MBBR, moving media in a tank. Other similar fixed film systems are trickling filters as well as RBCs. What we're going to focus on is a floating media-based system, where this is the internal surface area. So when we talked about the 900,000 square feet of surface area required, that's all this in here. And you can see the biological growth that grows here. This is a heterotrophic growth. It's very hairy. It would look like ciliates moving around in the water. And if you notice, there's no or very little biological growth on the outside of the media. And the reason why that is because as they move around the tank, they collide and they're hitting each other and rubbing each other off. So there's not a lot of biological growth on the outside. The way you control the sloughing or the biological growth is by designing your aeration equipment correctly so that those media collide into each other at a certain rate, so that as you're growing the biomass, it sloughs off and goes off out of the basins and into your clarifier. That's a critical part of the design in NBR, because if you don't have enough activation energy, you can actually get too much biological growth in there. And then the substrates, your BOD and your nitrification, as well as your oxygen bubbles, can't permeate into those spaces. Some of the earlier problems with this is they made the media too big. So if it was too deep, you would get very little biological growth on the inside of that plastic. You get some towards the outer edges. So basically you were buying plastic that was wasted material because it wasn't really doing anything. So getting the right configuration on that material is important. You'll see different designs of this from different manufacturers. This one here is made for heterotrophic growth with BOD reduction, and the openings here are pretty large. And heterotrophic growth has very thick biomass growth. You can get anywhere from 10 to 20 grams of biomass per square meter. If we were looking at a nitrification stage, and only nitrification, we would probably use a different style media where these pores here actually get smaller and you can fit more of them. For instance, this one has 650 meters per meter cubed of surface area, whereas a true nitrifying piece of media would have probably more like 820, 850 square meters, because the nitrifying biological film is a lot thinner. So it spreads out, so you don't need the wide gaps to get the substrates through. The other critical design in maintaining a fixed film system for BOD reduction and nitrification is the aeration grids. And I have two depictions here. One is in a circular tank and one is in a rectangular tank. And you'll notice in both of them that they both have full floor coverage of aeration grids. You want to have the bubbles moving up and around the tank so that media is being mixed all throughout the tank. It's critical that the media and the substrates come in contact with each other. So the way the aeration grids get designed is from really two stages. One, you have to get the correct amount of oxygen into the tank so that you get the BOD reduction and nitrification to happen. The second is you need the correct amount of activation energy to actually move that media around the tank. Depending on the application, you could go down to as low as a 25% fill fraction. So out of that tank volume, you'd fill up dry, you'd fill up 25% with the media. And that's to make sure that there's enough media that they're colliding with each other. The high end is around 70%. If you put too much media into the tank, they don't move around enough, so you can actually clog up the system. So between 25 and 70% is about where you want to run with a fill fraction on the media, and you have to have enough activation energy coming out of the aeration grids to move the media around. So in this particular application, we had about a 40% fill fraction in each basin, which is really an ideal sweet spot to be. So that's the aeration grids. The retention sieves, these can either be cylindrical, like this one is depicted, or a flat sheet, perforated or wedge wire screen. And that's where we were talking about 6 millimeter screening and the headworks coming down to here. We don't want anything that's going to clog up that screen, because if that screen clogs up, the tank level rises and the media ends up going up and out of the tank, which is not ideal. So that's a pretty good design. And from a hydraulic standpoint, the end wall velocity, the flow coming through the plant on a rectangular tank, you don't want it more than 30 meters per hour on the back end wall. If you get a long rectangular tank and you have it's just gushing through, it will push all the media down to one end and block up that screen. So that's a design consideration too, the tank configuration, particularly if you're looking at an upgrade to an existing activated sludge plant. You want to make sure that the flow going through those tanks is correct, that you don't get too much velocity hitting an end wall. You can set up these systems, although this presentation is set up around it for anoxic zones. where you can do denitrification. So much like an activated sludge system, you can set it up so that you have pre-anoxic zones, post-anoxic zones, depending on the situation. We use a banana-style submersible mixer, very low speed so it doesn't chop up the media. And the newest technology that's coming out for moving that a lot more energy conscious is the large bubble geyser style pumps, where they create those large bubbles that have very low oxygen transfer but great for mixing a tank. So that's another way you can do an anoxic zone. So this particular plant was set up for duplicity, so it has two trains coming down. Influent comes in here, and you can see the overflows to each basin. Inside, and I do have an aerial shot that you can look down in better, we'll see the retention sieves in the aeration grid. And the media would be floating around each one of these basins. The water flows through the retention sieves up a standpipe into this channel, which then goes into the next phase with two gates, so it can go to either or both tanks. Or if you had to do maintenance on a particular basin, you could shut that valve, you would still have 5 zones operating. So this plant was designed so that you could take a basin or a whole train offline depending on what you had to treat with. So an aerial view looking down, you can see the aeration grid. You're getting full floor coverage of the basin, so the media is moving around very nicely. And you see the retention sieves here that allow water and sloughed off biomass to exit the basin from one to the other and continue down through the train while holding the media back in the tank. As far as the aeration grid placement, you always want them submerged in the water. If they're half above the water, you will get bio-growth on the stainless steel or plastic, depending on what size system you have, and it'll end up occluding it. So you want the sieves submerged in the water so that the media is scouring them all the time, and that keeps them clean and open. And again, that comes down to the activation energy of mixing the media around the tank. So here you can see a stepped approach. There are actually different liquid levels in each one of these tanks, so it flows by gravity and without letting media go back out into these troughs here. So we'll get down to the actual plant characteristics. You can see here in the beginning, this is data spanning from August to October. So this is the end of the fruit season, and you can see we did have a couple of days where we had some spikes that brought it to near design flow. The flow and the load, when we get a few slides in, you'll see is very important for the surface area loading rate. And again, talking about how do you design one of these systems. If you were to look at an activated sludge plant, you're looking at cubic feet of volume and mixed liquor that you're carrying in that volume to get your work done. Here it's based on load in pounds of DOD or nitrogen coming in and how much can you load to the surface area. So peak design flow, not only from a hydraulic standpoint but also from a treatment standpoint, was critical in this situation. And then it tapers off a little bit, the fruit processing is done, and then the school is back up and running, so the flow is back up. Near peak design was 140,000, and they pretty much sustained that in the first couple of weeks of school. pH was not an issue at this plant. We did not have to add any alkalinity for the nitrification process. This is the effluent pH, and you can see it stays pretty stable, just hovering below 8.0, and that's without any additional alkalinity. So they were lucky there where they had to do a nitrification process, but didn't have to add any alkalinity. They're currently evaluating the need for DO feedback, and what they found is they have a pretty high residual DO in the basins continuously. So we're looking at putting in some DO measurement feedback control to the blowers so that they can ramp back the blowers and get some energy savings when needed. Currently, right now, they only have handheld measurements, and it's taken sporadically. But the data they have so far does show that they're up at a pretty high residual DO, so we're looking at cutting back some energy there. That'll be driven mainly by the nitrification process, not by dissolved oxygen in the BOD stage. So this is the influent milligrams per liter of soluble BOD coming in. You can see the fruit processor really drives this, up around 800 milligrams per liter, spiking, averaging down around 500 or 600 during normal process. And when they disappear, the influent BOD loading really drops down. There's not much coming from the school. So this process really had to be designed to handle some very changing scenarios. Again, when we talk about surface area loading rate, that's the square meters or square feet of the media in the tank and how many grams or pounds can you load to that. So you'll notice going back and forth between the soluble COD in milligrams per liter, taking the flow into consideration, and look at the surface area loading rate. The graph changes a little bit. You know, it's very similar to the milligrams per liter, but when we take the flow coming in, you know, we do get some bump ups when the school's coming around. So from a design standpoint, looking at milligrams per liter versus surface area loading rate, it's actually a little bit closer than it would first appear, but still very wide conditions that it has to meet. One thing that is nice about a MBDR system is you don't have mixed liquor return. So there's no return activated sludge. You're not balancing a mixed liquor. It's all done on the media itself. You could set up the same situation, which is called an IFAS, integrated fixed film activated sludge, where you're balancing a hybrid plant, where you're taking some media in the tank, but you're also carrying a mixed liquor. So you're letting two different bug populations kind of manage your scenario. That's a good application if you already have an activated sludge plant, you already have your return activated sludge pumps, etc. You can do a pretty easy retrofit and get more production through your existing basins than you could with just an activated sludge plant. The extra treatment capacity in the same volume with a maximum fill fraction is about 3 times higher than an activated sludge plant. So if you had a certain basin that was rated to take out 1,000 pounds on an activated sludge system, you could get about 3,000 pounds out with an MBDR system. So excellent for upgrading an existing plant. So if we go back here, we look at this variable load coming in, variable surface area loading rate, and we look at the effluent. This is their discharge effluent limit of 5 milligrams per liter, and you can see they're consistently well below that. Same thing with ammonia. Ammonia, you know, with the fruit processor, there's some ammonia coming in, not as much as when the school comes online. So varying conditions, self-regulating process as the BOD or the nitrogen comes in. The biomass will either grow and slough off more, or it won't replicate as quickly, and it's a self-regulating process. So there's no mixed liquor balancing, no return activated sludge. It's a one-through system. If we look at the removal rate, so this is a graph showing how many grams of ammonia per square meter are coming into the plant versus the removal rate of ammonia going out of the plant in the same one. And right there, apologies, that's a little small, but it's almost it's a 99.9% correlation, even when it's designed at near maximum loading of 0.3 grams of ammonia per square meter. It's still removing 99.9% of the ammonia. So very, very robust, very predictable way to treat wastewater. And to elaborate on that, here's your effluent ammonia limit, and this is the summer limit of 5.5. And there's the effluent ammonia, even coming down to very cold temperatures where we're in January, still well below their discharge limit. So varying flow, varying loads, varying temperatures, and at the end of the day, very robust treatment system. Any questions?
Your BODs were not a problem in the winter?
Not a problem?
Yeah.
They go down significantly if I go back to the chart here.
I might have missed that one.
So BOD coming in the winter is 224 milligrams per liter, very similar to a typical just municipal without a lot of industrial, up to 575 milligrams per liter BOD coming in really for about July to August. So it's a 3-month period where they have that high loading.
Was there a phosphorus limit or not?
There was a phosphorus limit because we were focusing on cold weather nitrification. I didn't put the phosphorus parameters in here. I believe their limit on this plant is 1 milligram per liter.
how did the system perform with that?
It's under that, yeah. It's, I think their last data was like 0.4, 0.5, something like that. All this data that has been taken in this data set here was out of the secondary clarifier. They actually retained the right to use those lagoons as post-equalization, post-holding, and discharge, so they can discharge seasonally. But they're not, in the design, they weren't expecting any treatment or any additional treatment, so.
That was my next question.
Okay.
What you were going to do, or what happened with the old lagoons? So they are going to be.
They left them in place and online as post-equalization and holding. What's the, usually in Minnesota it's 180 days? 180 days. I'm not sure what Michigan is, but I'm assuming it's around there as well. So take it.
Thought maybe they were going to turn it into municipal swimming hole.
Any other questions? Okay, thank you.
Thank you.